Kothari, Vice President of Ripple's Engitech Private Limited. Ajit Kothari, Vice President of Product Development, is a seasoned professional with over 32 years of expertise in power electronics. His career spans leading organizations such as Reliance Industries, Fuji Electric, and Rechem RPG. Sir has contributed to developing advanced systems like battery energy storage, solar converters, and high voltage equipment for renewable energy, electric vehicle, and utility scale application. With proficiency in handling high power and current, he is a visionary leader driving innovation and sustainability in industry. With this, I request our expert, Ajit Kothari sir, to kindly enlighten us with his words of wisdom. Sir, please.
Yeah, thank you, Archana madam, for the brief introduction. Uh,
Thank you.
so straight away, can we start the session or?
So, you can
You
start,
can
sir.
start, sir.
Okay, okay. Right. So I'll present the PPT here.
Okay, sir.
Is it visible?
Is it visible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah, I'm getting some echo from your end, I think.
Is it fine, sir?
Yeah, it is okay now.
Okay, sir.
Yeah, first of all, good evening, everyone. Uh, so this session is regarding the smart battery management system for electrical vehicle. So before I start this session, I hope everybody aware about the battery regarding the lithium batteries used in the electrical vehicle, because the BMS is part of that. Uh, um, it's a part of battery, including the BMS. So when we say a smart BMS, it is not only the protecting device, it is communicating the information related to batteries to the VCU in case of electrical vehicle, where VCU stands for the vehicle control unit. So all these informations are given to the vehicle control unit, and it is displayed on the monitor of the vehicle, where the SOC, SOH of the battery, again the you can say the charging during charging, discharging of the batteries. It is controlling the charging current, discharging current. It is monitoring the voltage of all the cells. So these are the basic requirement, or you can say the performance of battery management system. So we'll start with this. So first of all, when we say BMS, BMS is nothing but an electronic system that manages and monitors the performance of a rechargeable battery, ensuring its safe and efficient operation. So when we say it is how it is ensuring the safe and efficient operation means it is continuously monitoring the cell voltages. So battery bank is nothing but the series and parallel combination of the lithium ion battery cell. Generally nowadays lithium ion only are used. Earlier it was NMC. Now it is lithium ion. Mostly 90% are used in the electrical vehicle. So when we say a cell, it is 3.65 volt is the maximum voltage, and nominal voltage of that cell is 3.2 volt. So the BMS is continuously monitoring the voltage of each cell in the battery bank. Okay. So and the current flowing through that complete battery bank. Again, it is also monitoring the temperature of each cell, either each cell or maybe one cell from each module, so that if any malfunctioning is happening in the battery bank or any overcharging or during the discharging, it should not, I mean, damage the battery. That's the reason it is monitoring the temperature as well. So all these informations are computed and given to the VCU of your EV. So the another important function what BMS is doing here is the you can say the calculation or computation of SOC and SOH. So it is the SOC means a state of charge. So what is the charge present in the battery bank? So that it will give the information in percentage or in the form of bars. Like if you see our mobile, there also lithium-ion battery is there inside, and that information is available on our home screen. So the battery information is already, means it is in the form of SOC is always given, so that the user will come to know whether it is time to charge, or we can use that battery for how much time. So that way, this information is very important. And when this information of SOC is given to the vehicle, then it is up to the OEM. OEM in the sense the electrical vehicle manufacturer. If they want to convert this information into the kilometer, like let's say XYZ battery of AH capacity is giving, let's say, 100-kilometer range. So they can convert this SOC into the kilometer also, because let's say 100% SOC of battery is corresponds to 100-kilometer range of that particular vehicle. Then they can convert that percentage of SOC into the kilometer of the range can be given in by the vehicle. Similarly, what we are getting into the modern vehicle of CI type, combustion engine type, where the petrol or diesel engine are used, and that information of fuel is also given on the monitor. So how much kilometers are pending into the fuel. So same information means in the form of batteries also can be given on the data, means the dial of the vehicle. So this is the means general definition, application, and the purpose of the BMS, you can say. Application wise, other than this EV, these BMS are used everywhere, wherever these batteries, chargeable batteries are used. So, for example, in case of renewable energy, this battery energy storage system, we call it as BASE. There also this information is given. Then the portable devices like your laptop, your mobile. So there also this information or this BMS are used. In industrial equipment also, like UPS, inverter, there also these BMS are used. So this is the block diagram of a complete system, of a battery system, I'm saying, where if you see this, So these are the cells connected in series. So this forms the battery pack of a system, and the information, this dotted block is BMS. So all the information of cell in the form of voltage, current, and temperature is given to the measurement unit of the BMS. Then this information is estimated for the SOC, SOH of the battery bank. And then thermal management is also there, which monitors the temperature of the cell, whether it is within the limit or exceeding any limit. And that information is again passed to the outside control unit. In case of EV, it is VCU. Apart from this, one very important function of BMS is balancing the cell. So we will see this into detail when we go to the next version. So cell balancing is nothing but the all cells, whatever presents in the battery bank, should have the equal energy, so that you will get the maximum performance from the battery bank. So that is the purpose of having the cell balancing into the battery bank, and this is important function of our BMS. Okay. So these are the key functions of BMS. As I said, monitoring. So the important parameters such as voltage, temperature, current, it monitors these three parameters, and then SOC and SOH it calculates, because uh, these informations are not readily available, or you cannot measure it from the battery bank. So depending on the voltage and the current charged and discharged, the state of charge of battery can be computed. So this is again a algorithm part of that is BMS, which gives you the state of charge and state of health of the battery pack. So state of charge is very simple, which we understand how much charge is available in the battery bank. That is nothing but the state of charge. Now state of health is, let's say, my battery bank is of capacity of 100 Ah. Okay. Now, instead of 100 Ah, let's say after 2 years, 3 years, I'm getting 90 Ah. So the capacity of after 2 years is now 90 Ah. So the state of health is 90 Ah. So that is how we calculate again the SOC, because if your state of health is reducing, or we can say in our term it is degradation of the battery. So battery capacity cannot be 100% till its end of life. So end of life of lithium ion battery is around 10 to 12 years, depending on the number of charge discharge cycle. So generally, if we consider one cycle a day, it can the life of that battery bank is around 10 to 12 years. So number of cycles depends on 6 to 8,000 cycles we are getting in the battery bank. But during this 6 to 8,000 of life cycle, you will not get the 100% capacity from the battery bank. So that is what the SOH of the battery. Now the protection part. So protection again, it is preventing from overcharging of the battery. So if you forgot, maybe your the day to day is your mobile charging. Most of the people keep on charging on whole night. So mobile will get charged hardly in 1 or 2 hours now, because nowadays fast chargers are available with the mobile also. So if you forgot the, I mean, to remove the charger, BMS is there to protect the battery. So it will automatically switch off the power coming from the means from the charger. It will not give it to the battery. So inside MOSFETs are there that will switch off your charging current given to the battery bank. So that is how it is protecting your battery bank from overcharging. Similarly, for over discharging, let's say we have set the cutoff, let's say at 10% of our battery bank. So whenever this SOC is, let's say, 10% remaining, so your either your battery will give alarm to the user that your battery is going to die now or it is going to discharge. So it is giving keep on giving the warning for remaining 10%. And once it reaches zero, it will switch off your device. Either it is mobile, EV, laptop, whatever it is. So that cutoff point is also user friendly. So in our laptop or in our mobile, we can set that cutoff limit as well. For in case of emergency, if you want something that 10% can be saved for the reservoir, you can say. So in EV also, that additional capacity is always there. So uh, let's say 10% of that capacity they are keeping for reservoir. So once it is reaches to 10%, it will switch off your vehicle, and it can be used only for towing or running the vehicle for charging purpose. Then the overheating operating temperature, again, the lithium ion batteries are having a certain range of temperature where they are performing, or you can say they are operating at the maximum efficiency. So once that temperature exceeds, there is a danger of, let's say, explosion, or you can say the smoke will come from the battery. So to avoid that, this over temperature sensing is also part of BMS. Once it reaches to that temperature, unsafe temperature, it will immediately cut off the load. Either it is charging or discharging. So that MOSFETs will get switch off, and your battery or the battery bank is safeguarded from overheating. And the it again detect the fault, like short circuiting of your battery bank that will exceed the current limit. So it will change the current of output or input of the battery, and it will switch off the MOSFETs. Again, it is cell balancing also it is doing. So this is how the monitoring and protections of BMS or the battery bank is done by BMS. Now the remaining functions of BMS is balancing. So as I said, balancing is a very important function in the battery bank. So if your all cells are not at, let's say, at equal potential or equal charge, because all cells are connected in series or parallel. Let's say all cells are connected in series, and let's say 10 cells are connected in series. So 10 into 3.2 will give me a 32-volt battery bank. So if that cell is not means let's say one cell is either fully charged or complete discharge. So if it is complete charge, it will not allow me to charge remaining 9 cells, because one cell is already charged in that path. So it will not allow me the charging current flowing through that path, because all cells are connected in series. Similarly, in case of discharge, let's say one cell is completely discharged, 0%, but other 9 cells are having charge of 100%. Then again, that battery bank cannot be used for discharging purpose, because one cell is not giving the current. since all cells are connected in series. So that bank is useless, you can say. I cannot use it for charging purpose. I cannot use it for discharging purpose. So if cell is not means charge, I cannot discharge it. If cell is having full charge, one full charge, and others are not charging, either I'll not get the full capacity from the battery bank because other cells are not charged fully, and I'll not able to charge the battery bank because one cell is fully charged and it is not allowing me to charge the remaining cells. So the balancing of all the cell is very important. So again, in detail, I'll show you the balancing, how it is done in the battery bank. So this is the function of balancing, why balancing is important in battery bank. Another important function is the communication. So communication is very important to give the information of battery bank to the external world. Let's say by maybe CAN or IoT or RS485. So communication ports are available. So the way you wanted the information given to the external world or the monitoring devices or the display unit where this information has to be displayed. So that information is given to that device from the BMS. And then the diagnostic. So diagnostic is nothing but whatever means you can say the uh, issues in the battery bank. Let's say voltage is less or more, what happened to the battery bank. So you can go to the logs of the battery bank, which is available in the BMS. And from that, you can identify which cell is having issue, which cell is having more temperature. So it helps you in rectifying the battery bank. So it will give you the complete information of that battery bank, and you can easily detect the faulty cell from the battery bank, and you can replace that cell. And that's the I mean that's how you can diagnostic do the battery banks. I hope I'm not very fast in this.
Yes, sir.
Yeah. So once we finish, maybe we can have the question answer session as well. Otherwise, if you have any issues in between, you can just raise your voice and we can close that query there itself, right?
Okay, sir.
Yeah. So now the here now we will we just gone through the key functions of BMS. Where is monitoring, protection, you understood. Balancing and communication. These are two functions which we are going to means go through in detail. Otherwise, this monitoring you understood. It just monitors the voltage, current, and temperature of the battery bank. Protection again, it is protecting the battery bank from overcharging and over discharging. So balancing and communication part we will go in detail. So actually here we are closing the BMS functions, but we will go these two parts in detail now. So the communication with external system. When we say BMS is doing the communication with external system, is nothing but the information available with the BMS, like SOC, the state of charge and state of health of the battery bank, then individual cell voltage and pack voltage. Sometimes cell voltage is not required, but it is computing the battery bank voltage, and that pack voltage is communicated to the VCU in case of EV. So cell voltage generally it is not communicated to the means VCU, but it is having that log data available in the BMS. And we have another function as well, wherever, let's say in ESS, that cell information is also important. So there we are communicating the cell voltage as well to the external system. Current. Current is the charging current and discharging current of the total bank. So at what current it is charging, or at what current battery is getting discharged. So that is again, it is controlling also, and that information is also passed to the VCU. Again, temperature readings also. In some vehicle, if you can, these functions are available on the dashboard itself, where the battery temperature is also shown. Like, let's say now the battery temperature has reached to 60 degree or 65 degree. So that information is also shown on the dashboard, so that the user or the driver will come to know whether that battery is getting overheated because of the continuous run, or maybe during summer if he kept the vehicle into the sunlight, and because of that also the temperature of battery sometimes goes up. And when it is charging immediately, if he's started driving, so that time also it is very dangerous in case of EV. So that information is again given on the dashboard. So, and the fault warnings. So fault warning is nothing but the over voltage, over temperature, over current. These are the fault warnings. These are again available on the dashboard. Some way, other way, like over temperature is directly shown. Over voltage or overload, it is shown like fault with the battery. Or in terms of vehicle language, they will tell something overloaded or something like that. So this was the output data, what BMS is communicating to the external world. Now, regarding the incoming data. So incoming data means it is important during the charging of the battery bank. Let's say at what voltage I want to charge the battery bank, or at what current I should charge my battery bank. So that information is given to the charger, battery charger, or the EV charger. So this information is handshaken by charger and BMS, and accordingly that charger will supply the current to the battery bank or to the vehicle. Again, the thermal management is also controlled. So this information is again, sometimes it is not given to the charger, but it is given to the VCU, so that if required, it will stop the charging in case of, let's say, overcharge is done or over discharge is done. So in that case, it is again giving the temperature or the signal to the VCU. And the configuration settings, this is again, as I said, it is related to voltage. At what voltage, or what should be the charging voltage, what should be the charging current required by the battery bank. So that information is again given to the charger. Or at what voltage it is charging the battery. So that information is coming from the charger to the battery bank. So that is incoming for BMS. So BMS is measuring both the voltage and both the current. Both the current and both the voltage means it is charging current, discharging current as well, and the charging voltage and discharging voltage. So discharging voltage is nothing but the total voltage of battery bank. So that voltage is available for the VCU. And then charging voltage, again it is coming from the battery bank. So that voltage again, let's say my battery bank required 50 volt for charging, but charger is giving, let's say, 60 volt. So it will not allow the charger to charge the battery. It will give the signal like it is over voltage. So that protections are there inside the BMS to protect the battery. Now there are different application of communication. So in case of EV, now you understood how this information is given to VCU, what is purpose of that, and why it is required. So the other application like energy storage system. Now this battery bank is connected to the PCS, we can say inverter, and that inverter output is connected to the grid. So for EMS, it is very important. Like VCU in case of vehicle, EMS is energy management system where the information of battery bank is given to EMS. So EMS will understand the reservoir or the capacity available with the battery bank, and from that it can switch to the battery bank wherever or whenever it is required. So that information is again important from application point of view. Similarly, for consumer devices, as I said, the mobile, laptop, all these information, real-time data is always given to the control unit or display unit. So these are the application of communication. Now, how this communication flows in the EV. So the battery data transmission is done from BMS to the VCU on CAN bus generally, and the important parameters are SOC and SOH of the battery bank. So these two things are given on the CAN bus. Then charging coordination, again it is coordinating with the charger, whether what voltage charger should charge, what current charger should charge. That information is given to the charger, and then charger will accordingly feed the voltage to the vehicle. And this information again given feedback as a feedback to the dashboard of the vehicle. Now the second important parameter or the function of BMS is cell balancing. Now I already explained why it is required. Now the another important thing is hello, am I audible?
Yes, sir.
Okay, okay. So the cell balancing, why it is required? So this we already now understand why it is important. So voltage imbalance among the cell can lead to overcharging or undercharging of individual cell. So that is reducing the performance of the complete battery pack. So that's the reason this cell balancing is required. Now there are two ways how that battery bank is or the cells are getting balanced. One is the passive way of balancing the cell, where the excess charge of from the every individual cell is dissipated through a dummy load inside the BMS. Let's say I'm having 10 cell in the battery bank, and their charging range or the SOC range is maybe 50 to between 50 to 70%. So all cells will get discharged inside the battery bank up to the 50% of SOC. So that whatever whichever cell is having more charge inside, let's say one cell is having 55% of SOC, so 5% of charge will get dissipated from that cell. Another cell is having, let's say, 70% of charge, so 20% of that charge overcharge will get dissipated through that dummy load inside the BMS. Now, why it is important? As I said, if any cell is having more charge, that will not allow me to charge all the cell at 100% level. Let's say that 70%, if I don't discharge it, it will allow only to charge my battery bank for 30%, remaining 30% of the SOC. But only that cell is getting charged. That 70%, whatever cell was there is SOC cell, it is going to 100% and it is stopping the charging. What happened to other cells, which were at 50% earlier? Now, because of this 30% additional, their capacity will go up to 80%. So overall, your bank capacity will be at 80%, not at 100%. So that's the reason we are dissipating that extra energy from the available cell. That is the way of passive cell balancing. So extra energy will get dissipated. This is very simple circuit. So MOSFET and the dummy load is connected across each cell. And whenever this BMS is giving command to that MOSFET, that MOSFET will get on and that cell will get discharged through that resistance or the dummy load, and excess charge will get dissipated from that cell. So this is how we are dissipating the extra energy from other cell and keeping our battery ready for charging for full 100% capacity. Okay. Now the other important work is like it is active balancing as well. So active balancing means it is a little bit complex, but it is very efficient way of doing the cell balancing, because here we are not dissipating any energy in the form of heat or in form of loss to the battery bank. Instead of that, that additional charge is used to charge other cells. Like let's say in our earlier example, let's say one cell is having 70% of charge SOC, another cell is having SOC of 50%. So this, to balance these two cells, we have to remove this. Let's say average is 10%. So 10% of charge from 70% will be removed and given that charge to the another cell, so that both cell will be at 60%. So this is how we are balancing the battery bank with the help of active balancing. But in case of the number of cells are more in the battery bank, then this active balancing is little bit, you can say, complex system, where you have to identify the cell, which cell is having more charge, and then we have to identify the cell which is having lower charge, and you have to transfer this charge from one cell to that another cell. So this is little bit complex when number of cells in the battery banks are more. So this system, we are not using it right now for the bigger system where voltage levels are in the form of 50 or 60 volt. Means wherever cells are more than 16. So up to 16 cell, we can do the active balancing very efficiently, or you can say with the optimized circuit. But whenever number of cells are more, this design will get complex. So in that case, we are doing the, you can say, the balancing with the help of passive, or you can say the dissipating of heat or energy from the cell. So that is the simple way of doing the balancing for the bigger battery bank. This is the pictorial form of how the cells are getting balanced here. So if you see, these 4 cells are connected and having different SOCs. So this is without balancing, right? Now cell 4 is having complete 100% charge. So it will not allow me to charge other cell because this is already 100% charge. And since all are connected in series, it will not allow me to pass the charging current through other cells. Let's say in other example, all cells are connected in parallel. In that case, again, this voltage is there at the output, and my charger will come to know that yes, this bank is having full voltage. So that's the reason it will not allow me to charge another batteries, because this is stopping from charging the battery bank. Similarly, in case of discharging, now these cells are connected in series, let's say. So whatever charge is available in cell 2, up to that level, I can able to discharge this battery bank. Because after that, this will become zero and no current will flow through this battery during discharge. Similarly, let's say all cells are connected in parallel. So in that case also, whenever this battery or this cell is going up to zero level, you will get the full current, full discharging current. After that, it will keep on reducing the current because this cell already gone to zero level. Then let's say 3 cells are available. So these 3 cells will give the current to the load. Maybe after some time, these two will get zero, and then only one cell will give the current at the last. So there is a chance of this cell 4 getting over discharged, because whenever all these three are zero, still this cell is having some charge and it is giving the full current. Let's say my load current is, let's say, for easy understanding, 100 ampere. So each cell should supposed to deliver 25 ampere. But whenever these 3 cells are zero and my BMS is still allowing to discharge this battery bank at 100 ampere, this cell will discharge at 100 ampere. So it is 4 times the rated capacity. So I am over discharging this cell. So that will damage this cell. So this is how this balancing is very important. Now in passive balancing, as I said, all cells will be brought at the same level of this cell 2, because the excess charge we have to remove, so that my battery bank is at you can say the same level, and I can charge it or discharge it without harming the cell. So that is very important function of cell balancing here. We have to protect our cell. No doubt, we are dissipating the extra energy, whatever is available in other cells, but that will protect my other cells, or you can say the cell 4 in this example. I am protecting that cell from getting damaged by passive cell balancing. In case of active cell balancing, what I am doing now, I am transferring the excess charge from this cell 4 to cell 2 and cell 1 to cell 2, cell 3, sorry. And I'm bringing this all cells at same level again. So here, if you see this, this may be at, let's say 25%, but here I am getting more capacity, remaining capacity or reservoir capacity, I am increasing here without additional charging of the battery. So whatever charge is there, extra charge in other cells, I am using that charge to charge my under charge cell, so that my overall capacity of battery bank increases. In this example, it was 25% SOC, let's say, and here it has increased more than 25%, maybe 30, 40%. Right? I think with this, I come to the end of this session. I think I got a little bit fast since it was one-way communication. So we can go for question answer session now.
Dear participants, you can ask questions with any form. You can write in chat also. Hello.
Yeah,
Sir, could you elaborate on the role of ML in the BMS system? So the next advancement which can be done in the BMS system.
Okay. So, see, there are a lot of different types of BMS available in the market or in the industry. So, when we started using this lithium-ion battery bank, so that time very simple BMS was used, which is just to protect the battery bank from overcharging or discharging. You can say uh, the function was limited to protection of the battery bank. Now the need has come uh, when we started using the battery bank uh, to give that information to the user as well. Like what is the means the capacity is remaining, what should be the charging current, what should be the discharging current of that battery. So all these informations are available now. Whatever unknown battery, even you take an unknown battery bank, that information is given to the charger whenever charger is connected. That at what current it should charge the battery bank, at what voltage it should charge the battery bank. So all these informations are you can say pre-filled into the BMS, and whenever that handshaking is done with the charger, that information is given to the charger. Now these chargers are standardized uh, for the EV application, because now all vehicles are having different voltage, different capacity. So how that charger will come to know at what current I should charge, at what voltage I should charge. So that information is added into the BMS now. Earlier it was not there. Now since the application wise and in India, unfortunately, we don't have the standardization of battery bank. If you see the four-wheeler vehicle or even two-wheeler vehicle, all battery banks are having different voltages, different capacity, uh, because all OEMs are manufacturing their own battery bank, because their own motors is uh, they have their different motors used for the vehicle. So they require different DC voltages. So this is very unfortunate in India, because we not started with standardizing the battery banks. Now here we cannot replace the batteries also with from one vehicle manufacturer to other vehicle manufacturer. Let's say example of two-wheeler is very simple to explain. I cannot remove the battery from the vehicle here, and I cannot just go in market, buy that battery, put it into the vehicle, same like our lead acid batteries, because there we have the standardization. We have the same size of battery. You can replace with any other make, but unfortunately in lithium ion, that because the standards were not available initially, nobody thought of having the standardized batteries. So I think that area we need support from government as well, because to standardize the battery, again, I think in Europe, they are now doing this exercise, similar to what the charger we have now done for the mobile application. Now that pin is standardized, at least. So similarly in chargers, now that only the sockets are standardized, not the battery size or battery capacity or uh, the dimensions of batteries are different for everybody. So that area is challenging for us also, because as a manufacturer, we are not able to keep that batteries in stock, like off the shelf. Like anybody is coming and using that battery into their vehicle, similar to lead acid batteries. So that is the one disadvantage of this technology at present in the India. And we are discussing with the government as well on this part. But now, since this is one hand, this technology is under development, under expansion, so everybody is using their own what you call the available resources, available whatever the designs they have. So that's the reason the standardization is very difficult right now. So that is one part in the lithium ion battery. Another is the temperature range of that battery bank. So here I think we should have, maybe, because if you see in India, our temperature in some region it is going up to 55 degree as well. So there you cannot just simply drive this EV, because the temperature there itself is 55, and if I drive this vehicle there, and the delta or the temperature rise of that battery bank is, let's say, 20 or 25 degree, it is exceeding my safer limit of that battery bank. So I cannot means use that battery beyond 65 degree. So up to 10 degree is the margin where I can use that battery. Similarly, at the lower temperature also, when temperature are going, let's say, below 10 degree or below 0 degree, I cannot charge the battery. I can discharge the battery up to minus 20 degree, but I cannot charge the battery at, let's say, 0 degree available. So in case of Kashmir or the Himachal Pradesh, where temperature is going below 0 also, so there charging is a challenge. So there we are putting additional heating element into the battery. Whenever the temperature is going below, let's say, 0 degree, and you want to charge your battery, you cannot charge simply. You have to just heat up first that battery bank, and then you can charge the batteries. So these are two limitations from temperature point of view in the lithium ion batteries. So I think the budding engineers can work on these two things, where we can have the optimize, or we can increase the safe, or you can say the temperature limit of the batteries, which is right now for discharging it is minus 25, 20 degree, and up to 65 degree. So this is discharging range, and charging range is 0 to 55 or 60 degree. So that is my charging range. If I could able to increase this range, then I can use that battery bank anywhere without adding additional cost into the batteries. So right now, if you want to use that battery, let's say for cold region, I have to give additional heater. And if I want to use that batteries uh, in hot region, there I have to give some cooling, additional cooling to the battery. So these two things are additional to my battery bank, or you can say the battery cost. So these two basically are the challenges right now. Another is the you can say the charging infrastructure. So whenever I am increasing the capacity of vehicle, let's say I want to make a vehicle with bigger range, let's say 400, 500, 600 kilometer range, I have to use a bigger battery into the vehicle. So using bigger battery into the vehicle is not the challenge right now. Challenge is the charging infrastructure required for charging that batteries, bigger batteries. Now the Tatas and the Hyundais are coming, or even I think Maruti is launching this new vehicle with 100 kilowatt hour battery inside. So 100 kilowatt hour battery, if I want to charge, let's say within 2 hours, I need a minimum 50 kilowatt hour of power available with me. Then only I can charge within 2 hours. Now people are asking for 15 minutes charging of the vehicle. So if I want to charge that 100 kilowatt hour battery within 15 minutes, I need 400 kilowatt hour power. Then only I can charge that vehicle. So the charging is not the challenge for us. We can charge with the higher power also. We can manufacture the higher kilowatt hour batteries also, but the challenge will come into the infrastructure, because to charge at higher rate, I cannot use my residential power or society power for charging that vehicle. I have to go to some station, charging station. I have to wait for 10-15 minutes. Then only I'll be able to charge there at fast rate. Otherwise, I have to bring at my home, maybe at society with nominal charge, or I can charge it within 3 hours, 4 hours. So that is how the industry is now changing from charging perspective. So I think these 2-3 challenges are there where we are working with the system as well, with the government as well. We are requesting for charging infrastructure so that this industry will get boom. Now people are using these batteries for truck as well. So there are 2-3 companies where they already started developing the battery bank. We already started developing battery bank for them. So there the capacity of battery bank is in the range of 200 to 250 kilowatt hour. Now you can imagine once these trucks start rolling onto the road, and they need this much power. Already buses are there, but buses they are going into their depot at the night time, and they are kept idle for charging. So 4 to 6 hours they are keeping that bus for charging, and then remaining time they are using it, or daytime they are using it. So bus is exceptional. But when I'm talking the truck is supposed to be on the road 24/7, right? Because they are having the extra driver with them. So they are keep on running the truck. And to keep the truck running, I have to charge it very fast rate. So 250 kilowatt hour of battery bank, if that bus or that truck is having, I need minimum 500 kilowatt hour power to charge that truck within half an hour. So double the rate I am saying, double the rate, so that I'll charge within half an hour. So half an hour also, it is very big, means from the charging point of view. When I am going for fueling with the diesel or petrol, within 5 minutes they are filling my tank, I am ready to move. But the charging of bigger vehicle is going to be challenge unless we have the sufficient the infrastructure, or the infrastructure with high power. So I think these 2-3 challenges are there in this industry, which we are coming, or we are discussing with the industries as well, with the government also, how to provide this. Now maybe tomorrow again we are having one more session where we will be discussing how to integrate this renewable energy with this EV charger. So we can say this is the background where we will discussing tomorrow on this topic as well.
Any questions from the side of your audience side?
I think Dr. Minal, this
Yes, sir.
online discussion, no, that feeling is not coming when
Yeah,
we,
yeah, yeah, yeah. In future, sir, definitely we will planning. Okay.
yeah,
If it
because
is
when
possible,
we
then
interact personally in front, no,
offline we
then
will do. Okay.
correct.
Sir, in chat box, there is a question. You can see.
1 second.
And Amit Srivastav also raised his hand.
Yeah, you can ask. Yeah, Amit.
Sir, but as you suggested that the companies are trying to or moving towards the fast charging system, but the fast charging is also there is a problem with the fast charging that the for the life of the battery system, no?
Yeah, so, see, requirement, now we have to go with the requirement of the user. Let's say I'm using this battery for a bigger application. Let's say EV. If I am taking the example of EV, if I'm buying a four-wheeler with this battery pack, and if I'm not able to charge my battery or my vehicle, let's say within 15 minutes, 15 minutes also I'm saying on the safer side. 15 minutes means I have to charge at 4C rate, 4 times the capacity of the battery pack. So when I charge with 4C rate, then only I am getting the charging within 15 minutes. Yes, no doubt. As you said, the degradation of batteries will get more faster if I'm using at faster rate. But the OEMs, the cell manufacturers are coming with that solution also. If you, I don't know whether you heard LTO. These LTO cells are coming with 8C application. So 8C application means within, I think 7.5 minutes, I could able to charge the battery at 100% from 0 to 100% within 7.5 minutes. So that is what the battery manufacturers are coming with the challenges. So these are taken care into the batteries. But what about the infrastructure? If I want to charge, let's say, same example, if I take 100 kilowatt hour of my vehicle battery, if I want to charge at 8C, 8C means you can just imagine it is 800 kilowatt hour power is required for 7.5 minutes. Then only I can charge that battery within 7.5 minutes. Since I don't have the charger, I am limiting myself with slow charging. So it is not like sales are not available. Sales are available. But since infrastructure is not there, we are not using that cell for the proper use. If you go to this Tesla or some other BYD in China, they have the cell available with them. It can be charged at 4C rate also. So 15 minutes, within 15 minutes, they will charge your truck or your bus or your car. Within 15 minutes, it will get from 0 to 100%.
And sir, what is the cost difference between these two?
Cell technology now, see, this lithium ion is now, it is almost matured in India also. And we are getting this cell, let's say at $80 per kilowatt hour. And the LTO is double the price, since the mass production is not still happening, the cost of that cell is double. So once we get that demand, or once it started increasing in our use, then that rate will come down. Similarly, in this lithium also, if you see this, 4 years or 3 years back, it was almost $150 per kilowatt hour. Now it is come down to half. So it again depends on the demand. If you increase your uses, the price will come down.
Thank you, sir.
Sir, in chat box, Dr. P.N. Rajan Ramayan.
Yeah. So what innovation in BMS are driving the development of net zero energy building?
Rajan.
So I read the question. So here the net zero energy building, I think from BMS point of view, if you see, it is the during cell balancing only. So as I said, cell balancing we are doing with the two different ways. One is with passive balancing, and another is active balancing. So if we are able to do with active balancing, that will give me the net zero energy building, because I am not wasting any energy from the battery bank uh, as a heat or as a loss from the battery bank, because I already given that power to the battery bank to charge it. So whatever additional power means, at one hand I am charging the battery bank, and on the other hand I am discharging it inside, because I want to balance the cell. So this is net zero energy will be effective only if I use the active balancing very effectively, because there I am not wasting my power. Whatever power is charged inside the batteries, I am distributing equally inside the cell, all cells. So this is the function of BMS. But from the vehicle point of view, or you can say the charging infrastructure point of view, there this renewable energy will come into picture, because there I don't have to. I mean, if I am saying zero carbon, so I should not generate power to charge the battery. If I am generating any power to charge the battery, then I am not zero carbon level. I should generate that power from renewable sources, so that uh, I am means reducing the carbon production. So these are two different things where you can say this reduction in carbon to charge the batteries is important, because when I'm using that battery, I'm not producing any carbon, or I'm not polluting any environment. But to charge the battery, definitely I need a power, and that power, how you are producing or how you are generating, is important. If you are generating with renewable sources, then it is 100% green energy. But if you are using your normal power, which is generated with the coal thermal power station, then it is not a zero carbon or zero wastage of that energy. Even though I'm while using that vehicle, I'm not producing any carbon, but to charge the vehicle, I'm using the carbon. I hope I clarified this net zero energy building.
Okay, sir. I think it is. He has written. Thank you, sir. Okay, thank you, sir.
Thank you.
Thank you for your this nice session. So tomorrow we'll again meet, I think. at 2 p.m. I think 2 or 2:30.
We'll make it 2:15. It is, I think, at 2 o'clock.
Yes,
But
sir.
since it is lunchtime of everybody in our office as well, so
Okay.
maybe we'll delay it by 15 minutes. So we'll
Okay,
start
okay.
at 2:15.
Okay, sir, no problem. Dear participants, so today's session we have concluded now, and for tomorrow, we will take 15 minutes extra, means 2:15. By 2:15 we will join.
Okay, sir. Okay, right.
Right.
Okay, sir. Thank you. Good night.
Thank you. Thank you all for joining.
Thank you, sir. Good night.
Thank you. Good night.